Can you all see my screen that side, sir? Hello?
Yes. Also,
Okay. Thank you. Let me just do this. So should I wait a bit for them to join, or can I just start now?
I think you can, because these are members of parliament. They know 8 o'clock is 8 o'clock.
Okay, so not a problem then. Thank you. I can start. Hello guys. Is there any of the creators who are already in the session?
I'm in grade 12, sir.
Yes, so all of them are in grade 12.
Okay. Hello guys, my name is Mutsutsana Makhema, but you can also call me Tlo. I think maybe Mr. Desmond already maybe told you about me. I'm just going to be with you for some time with mathematics. From today onwards, I'm not sure until when, but for some while time, Yana. So he just instructed me to start with Euclidean geometry today. So I also requested if I can be able to start with grade 11 revision, because I think it's also important because they also assess grade 11 Euclidean geometry in grade 12. So this is the textbook that I'm using now. It's Mind Action Series for grade 11, just to remind ourselves with the basics of Euclidean geometry, whereby we are going to focus on lines, angles, and triangles, and other quadrilaterals. So the first thing that you're going to look is the first structure that we are seeing there on the screen, which is just a line and another line that intersects with the horizontal line. It divides that 180 degrees in two angles. So this, okay, from grade 7, I think, or 8, we know that a angle on a straight line forms 180 degrees. So every angle, when you take those angles and you sum them up, you are always going to get 180 degrees. Then that can be your reasoning when you're reasoning, because remember, in Euclidean geometry, everything or every calculation that we are writing must be supported with a reason. We don't assume in geometry, we support using a Euclidean geometrical reasonings. So if you take angle B2, you add angle B1 is equal to 180 degrees, then why? You provide a reason, because those angles are supplementary, or angles on a straight line are supplementary. Still keeping in mind that supplementary means they sum up to 180 degrees. I hope it makes sense, guys. Then if also I'm moving too fast, please just let me know to reduce the speed a bit. If again I'm moving too slow, just let me know to increase my pace a little bit. Then we can go to the second structure or second diagram, angles around a point, or the revolution, just a circle. So the revolutions make a 360 degrees, meaning if you take your angle A plus angle C plus angle B, you're going to get 360 degrees. You have to know all these things, guys. We're going to use them a lot. Then we go to the third structure, which is X. So every time in geometry, when you see X, just know that opposite angles are equal. Note that those dark dots are the ones that are opposite, and those plus are the ones that are opposite. You can't say that dark dot and this plus circle are opposite. You need to just, I think, understand this X thing. The opposite angles needs to be equal. Then we go to the fourth structure, which is for the corresponding angle. And please note that for corresponding angles, for alternate angles, also for cointerior angles, you can't state those reasons if you don't have parallel lines. You can only state those corresponding angles, alternate angles, co-interior. You are given some, sorry, a bit with that. I'm sorry, I will just resume later. So I was saying to you, you can't reason if you don't have parallel lines. For corresponding angles here, x is equal to x. And then after you said x is equal to x, you state your reason, corresponding angles. And then after corresponding angles, state your parallel lines that AB is parallel to CD. Same applies with this fifth diagram. You are going to say that x is equal to x, alternate angles. After stating that alternating angles, state which lines are parallel. AB is parallel to CD. Always remember to state also those parallel lines. Then for the sixth diagram, for cointerior angles. For cointerior angles are supplementary also. Meaning if you take that x and y, you add them, you are going to get 180 degrees. So you are going to reason that saying cointerior angles. And remember, after you stated your reasons for parallel lines, you have to state which are those parallel lines. AB is parallel to CD. Then you also, I think it's also wise for you to know quadrilaterals and its properties. But now we are talking about, okay, scalene. What kind of a triangle scalene is? So the scalene is a triangle whereby all sides are unequal. Then we also move to the second one, which is the isosceles triangle. We are going to use this a lot. So the isosceles triangle is a triangle with two sides that are equal and two angles that are equal. Then we move to the next page, 208. We have this this triangle on the top left corner. It is equilateral triangle. Equilateral triangle is the triangle with all sides that are equal and all angles are equal, which will always be 60s, because those 60s will add up to 180 degrees, as we all know that the sum of all angles in a triangle are supplementary. What do we mean by supplementary? When you add them all, they give you 180 degrees. Then we have the right angle triangle, of which I think we're also going to use it a lot in geometry. So the right angle triangle is a triangle that have got 90 degrees within its triangles. Then we move to this triangle that is right below the equilateral triangle. Then it just summarizes, I think, what I just said before, that if you add all the angles of a triangle, you're going to get 180 degrees. Then we move to the triangle that is right below the right angle triangle, whereby we can see there is some line that is extended from that angle A, then it passes at angle C, and then outside a little bit of the triangle, whereby we are going to have angle C as equal to the sum of A plus B. Then your reasoning is going to be exterior angle is equal to the sum of interior opposite angle. I think we're also going to use this a lot. Then we also have Pythagoras theorem, I think, from grade 6. And you should note that because I think some students, wherever they see a triangle, they always use Pythagoras theorem to calculate the unknown side, maybe. But I don't think that's correct. That is mathematically incorrect. You only have to apply a Pythagoras theorem on a right-angled triangle, whereby if you are going to sum the square of the other sides, the subject of the formula squared is going to be the hypotenuse. then you can work around that mathematically transposing, keeping in mind that if you transpose something to the other side, the sign changes, sorry. If it was positive, it's going to be negative. If it was negative, it's going to be positive. Then we can move to congruency of triangle with 4 conditions, whereby condition 1 is saying these 2 triangles that we are seeing, the first 2 triangles, are congruent if 3 sides of those triangles are equal. That's where we're going to use side. Then condition 2 is if two triangles are congruent if 2 sides of those triangles are equal and 1 angle on those triangles are equal, then it's going to be congruent. Meaning it's going to be side. Then you're also going to have a condition 3, 2 triangles are congruent if 2 angles and 1 side of a triangle are equal to, I think it's angle. Yes. Then the 4th condition, 2 right-angled triangles are congruent if the hypotenuse and 1 side of the triangle and the angle are equal. Then those triangles are equal. Then moving like that, you're going to have also the midpoint theorem, I think from grade 10, whereby you've got your triangle, and this triangle, when you check the proportional of the side, like when you check on your left side of the triangle, is going to have 2 equal sides. And also when you go to the other side of a triangle, there's going to be 2 equal sides that are divided into 2 equal proportions. Then that implies that if DE is parallel to BC, then DE is simply going to be the half of BC. So I think that only happens if AD is equal to DE and AE is also equal to EC. That's only when you can say DE is the half of BC. Then we also going for the properties of the quadrilaterals. I think it's the best for you to know all the properties of the quadrilaterals because we're going to use that a lot in geometry. So firstly, when we look at this parallelogram ABCD, you need to know the properties of the parallelogram. You need to know that opposite sides of a parallelogram are equal. You also need to know that opposite angles of a parallelogram are equal. Again, you need to know that opposite sides of a parallelogram are parallel. That's what you need to know. So in this parallelogram that we are having here, because AD and BC are opposite sides, they are equal and they are parallel. BAB and CD are opposite sides, they are equal and they are parallel. Therefore, we can conclude now by saying A1 is equal to C2. Your reason can be alternate angles. Why? Because AD is parallel to BC. Or you can play around your maths. D2 is equal to B1, alternate angles. You state also your parallel lines. Same applies with the rectangle. You need to know the properties of the rectangle, properties of the rhombus, properties of the trapezium, properties of the kite, because we are going to use that a lot. Then now we need also to know how to master the parts of the circle. You need to know the terminology of what the radius is, what the diameter is, what the chord is, what the circumference is, what the center of a circle is. So in this diagram that I'm having right on the screen here, I'm having the circle with some parts of the circle, and on the box just right next to the circle, I'm having some few definitions of some parts of the circle. So we have the radius in a circle, and we all know that the radius is the line from the center of the circle to any point of the circumference. Then we also have the diameter. The diameter is the line passes through the center from another point on the circumference to another point on the circumference. That's the diameter. And diameter is twice the radius of the circle. Meaning if I'm saying to you, the radius of the circle is x, then diameter is obviously going to be 2x of this circle. But if sometimes you are given a diameter and you want the radius, the radius is just the half of the diameter. If I'm saying the diameter is of the length of 4x, then what's the radius of the circle? The radius is just going to be the half of that 4x, which is just going to be 2x. Then we also have the chord. The chord is the line that moves from any point on the circumference to the other point on the circumference, and that line doesn't pass through the center. That's where you can differentiate a diameter and a chord. Then we also have the segment right here. So the segment is that shaded portion between an arc and the chord. Then we also have a sector. It's also that shaded part right within those radii, because remember the plural of radius is radii. So that shaded part is the sector between those radii and the arc. Then we also have the secant, which is the line that cuts the circle. Iona is not the line that moves from any point on the circumference to the other point of the circle. It goes out of the circle, cuts the circle. We also have the tangent, I think, which is we are going to use a lot in geometry. A tangent is the line that touches the circumference of the circle only at one point, just like we can see this tangent, it touches this circle at that point. You need to know these terminologies here. Then from there, we can just move to those nice theorems that we have learned in grade 11, from theorem 1, I think, up to theorem 11. So theorem 1 is saying that if the line is drawn OM, where O is the center, to the point M, and is perpendicular to that chord AB, then you can conclude by saying AM is equal to MB. You need to know these reasonings because you're always going to write the statement and reasoning. The mark for the reasoning is the mark for the statement. So if we just write in the statement without the reason, we're not going to get full marks. Then that theorem 1 also have the converse. In sometimes, because you can be given that AM is equal to MB, then if that's the case, you know that the converse is that OM is going to be perpendicular to AB. That's what theorem 1 says. Then we can go to theorem 2, and then theorem 2 is just right here. Theorem 2, in short, is stating that angle at the center is twice angle at the circumference, or angle at the center is 2 times angle at the circumference. If you are given an angle at the circumference there, because you're going to be given something just like this, I don't know what shape is this, but you are going to be given something like this. Let's say you are given an angle C in this case. In this circle, let's say you are given an angle C as angle X. Then they say to you, find the angle AOB. So angle AOB, you know that is going to be 2 times angle ACB. Your reasoning is going to be angle at the center is 2 times angle at the circumference. Then remember, just a little bit of a reminder, sometimes you can be given an angle at the center and then they say, go find that angle C, and then they give you angle O here. Then you are just going to divide this angle O by 2, because now you want that angle at the circumference. Then this is the proof to that theorem. I think it's also wise for you guys to know the theorem, the proof of these theorems, because it is also accessible. It's 5 marks, I think, so it's a very, very good mark. Then we can just move to the third theorem right here, whereby in this diagram of ours, you can see a circle. You can see we've got a diameter A O B. We've got angle C right there. So according to the theorem, angle C is going to be 90 degrees. Then your reasoning is just going to be angle in a semicircle, in short. Angle in a semicircle. Then this is just the proof of it using the theorem 2 that we just talked about recently. Because we know that angle AOB is 180 degrees. Then how can we want angle C? Because angle C is on the circumference, is going to be the half of this angle at the center, which is 180 degrees. So half of this 180 degrees is going to be 90 degrees. So angle C is 90 degrees. So every angle that is going to be subtended by a diameter is always going to be 90 degrees. You need to note that. Then we have the converse of theorem 3, that if the angle subtended by a chord at the point on the circle is 90 degrees, then that chord is the diameter. You also need to keep that converse in mind. Then we can move to theorem 4. Theorem 4 is saying an arc or the chord of the circle subtends equal angles at the circumference of the circle. We say that the angles in the same segment of the circle are equal. We just, for this one, I think if to remember this, I always use to say, I always use to think of a bow tie shape if I want to identify these angles in the same segment thing. I always think of a bow tie. Then you can say those up angles, these angles in a, sorry for that. And then angle A is equal to angle B, angles in the same segment too. You can say angle B is equal to angle D, angles in the same segment. It doesn't work like that. Also, you can say angle D is equal to angle B and then say alternate angles. Why? Because there is nothing that told us that AD is parallel to BC. So you can't use alternate angles, corresponding angles, or co-interior angles. And then afterwards, we are just going to move to the next theorem. Okay, these are the corollaries of theorem 4. These are some options or possibilities of how those that theorem can be assessed. You can be given something like this, and you know that equal chords subtend equal angles at the circumference, or just equal chords subtend equal angles. Same applies with this, equal chords subtend equal angles. Same applies. These chords are equal, they subtend equal angles. And those angles are always opposite those chords that we are talking about that are equal. They are always opposite those chords that we are talking about. And then now we can move to the next section, which is the cyclic quad. So a quadrilateral whose vertices lie on the circumference of a circle is referred to as a cyclic quad. A, B, C, D in this circle is referred to as a cyclic quadrilateral. In short, a cyclic quad. We are going to use this word a lot in this geometry. So this theorem 5 is saying the opposite angle of a cyclic quad are supplementary, keeping in mind that supplementary means their sum, it's 180 degrees. So in this case, angle D plus angle B is going to be 180 degrees because those are the opposite angles of this cyclic quad. Angle C is equal to angle C plus angle A is equal to 180 degrees. Those angles are supplementary because they are the opposite angle of a cyclic quad. Then this is the proof of this theorem. You also need to know this proof of this theorem using that theorem 2, angle at the center is 2 times angle at the circumference. We also have the converse of this theorem that if the opposite angles of a quadrilateral, it is not stated that these opposite angles of a cyclic quad, it's just stated that if the opposite angles of a quadrilateral, of any quadrilateral, are supplementary, then the quadrilateral is a cyclic quad because opposite angle of a cyclic quad are supplementary. Then we can move to the next theorem, which is theorem 6. It's saying an exterior angle of a cyclic quad, which is that angle C1, is equal to the interior opposite angle, which is that angle A. So angle C1 is equal to angle A. You state your reason. An exterior angle of a cyclic quad is equal to interior opposite angle. Then also the converse is saying if the exterior angle of a cyclic quad is equal to the interior opposite angle, then you can conclude by saying that quad is a cyclic quad. Then we can move to the other theorem, which is the theorem 7. In this theorem, we can see that we have got a tangent to a circle. Remember that the tangent is the line that touches the circle on the circumference at one point. In this case, the point is B. Then we also have the radius. Remember, the radius is the line from the center to any point on the circumference. Then the point of ours here is B. So this theorem is saying a tangent to a circle is perpendicular to a radius at any point of contact. Where those two lines meet, that radius and the tangent meet, there will always be that perpendicularity. There will always be 90 degrees there. Sometimes they can just give you a diameter, maybe let's say KOB. You still can use that. Diameter is perpendicular to tan. We also have the converse of the theorem. If a line is drawn perpendicular to a radius at a point where the radius meets a circle, then the line is the tangent to the circle. We're still going to use that a lot. Then we can move to theorem 8. Okay, this is saying if two tangents, knowing that tangent is the line that touches the circle at one point. So in this case, there are two tangents, and these two tangents are drawn from the same point. In this case, that point is A, from the same point outside the circle, and they are equal. These tangents are equal in length, meaning AB is equal to AC. That's what this theorem is saying. Then this is the last theorem, I think. Yes, it is. So this theorem 9 is saying the angle between the tangent and the circle, or I mean the tangent to a circle, and a chord drawn from the point of contact is equal to the angle in the alternate segment. In short, it's a tan chord theorem. You are allowed to just say, maybe if you said angle X is equal to angle A1, your reasoning can be just tan chord theorem. I think you can get full marks with that. Then in this case, in this diagram that we are having now, is that theorem is stating that angle B2 is equal to angle E2, tan chord theorem, or angle ABE is equal to BDE, tan chord theorem. Then we also have the converse of the theorem. The converse of the theorem is saying, if the line is drawn through the endpoint of the chord, if the line is drawn through the endpoint of the chord, making the chord an angle equal to an angle in the alternate segment, then the line of the tangent to a circle. Then the reasoning for that can be just the angle between the line and the chord. Then you get your marks. Then I think now I should just show you how to use these theorems, maybe whereby we have a complex of some questions. I think I have something right here. Where is it? Maybe I can just say just hang there with me. I'm just going to find some questions. I've got this question right here. So I think I am going to use a camera because I have to write something down too. But can you all see what I've shared now? Hello?
Yes, sir.
Okay. So in this question, they are saying, in the diagram below, the tangent KT to the circle, keeping in mind that the tangent is the line that touches the circle at one point. So in this case, it touches the circle at the point K. And this tangent KT is parallel to the parallel to the chord NM. Full stop. That parallel thing, you need to note it. It can help you to use alternating angles, corresponding angles, and the cointed angle somewhere. Then full stop, NT, where is NT? NT, cut the circle at L. Then triangle KML is drawn, and the angle M2 is equal to 40 degrees, and MKT is equal to 84 degrees. Then what I'm going to advise you guys to do, let me now maybe share the camera. Now how do we share the camera here? I'm stuck. And then I want to share the, okay, let me just do this because I can't find some tab to. Yeah, can you see my screen now?
Yes, sir.
Okay. So every
Yes, sir.
time, so I'm going to say to you, every time you get to that grade 11 Euclidean geometry, after reading your statement, what you're going to write down is DRCPT. In order for me to remember it, I always think of Dr. Cape Town. Dr. Cape Town. DRCPT in short. So this DRCPT, you will mark everything on the question paper that you are having there, and then just mark it, use it, and then when you get to the question, most of the question will be answered. Where this DRCPT, whereby this is the diameter, this R is the radius, this C is the cyclic part, and then this P is parallel lines, and this T is a tangent. So what you do when you get to,
Hello, sir.
to the,
Can you hear me?
yes, I can say.
Okay. I wanted to check if somehow we can make an adjustment on what is it? You see on your screen there's that 0.5. It's on 1 times. I want to check if we can
This
zoom
one.
out. Okay, it has zoomed out, but I'm curious to know if everyone is able to see.
Okay. Can you all guys see?
Yes,
It
sir.
was better at once, sir.
It was better at 1.
Yes,
Okay.
sir.
No, then it's fine. Yeah, I think it was better at 1 because
So can everyone
at
see
1
now?
is zoomed in. Okay, no, then it's fine. They will communicate in case if it
They
doesn't
can't
show
see.
everything that you're writing. Okay, no, thank you, sir.
Okay, not a problem, sir.
Sir,
So
why
as I
don't you
was
just
saying,
tilt it on the side so that it can show the full view?
sorry,
Why don't you just tilt the phone like
you want it to
hold
be like this?
Yeah, now it shows the full thing. It's better.
Is it okay?
Yeah, I guess.
So can everyone see now?
Yes, sir.
Okay, then I think we can move. So as I was saying, every time when you get to the question paper, to those grade 11 questions in Euclidean geometry, you just need to write this maybe on your question paper, DRCPT, whereby this D is for the diameter, then the R is for the radius, then C for the cyclic quad, P for parallel lines, T for the tangent. Then you check on your diagram if there is any diameter, and then you just highlight anything on the diagram that you know about the diameter. What the diameter implies, there is this theorem that involves the diameter in this Euclidean geometry. The angle in a semicircle, there might be an angle in a semicircle that can be 90 there. Then you move, if there is no diameter, you move to R, which is the radius. You also go for something that you know that it can help you. We know if there's a tangent and that tangent intersects somewhere with R at the circumference, you are going to have some 90 there, which is the radius is perpendicular to the tangent. Then with radius too, we've talked about isosceles triangle. Sometimes you can have something like, okay, this is our radius. This is another radius of mine. I've got a chord here, then the center O, and then what's not happening? I'm sorry for that. I've got the center O, I've got the point A on the circumference, I've also got the point B here. So we know that this is the radius, we know that this is a radius. Therefore, this angle will be equal to this angle since this is the isosceles triangle. Therefore, equal angles, opposite, equal side. Then after you are done with the radius, you can just move to the cyclic quad. And then if there exists a cyclic quad in your diagram, you apply every property that you know about the cyclic quad such that you maybe answer some questions that you're going to find on the question. Like opposite angle of a cyclic quad are supplementary, or the exterior angle is equal to the interior opposite angle. Then you can also look for some angles that are in a same segment. Then if you are done with that, you can go for P. If there are some parallel lines in your diagram, then you go for this technique. Math is fun. If these lines are parallel, then you know that these angles are equal, corresponding angles, and then you state your parallel lines that maybe AB is parallel to DC. Then if also they form something like you know that these angles are supplementary, meaning they add up to 180 degrees. And don't forget to state your parallel lines. also if they make something like Z or N, which is alternate angles, then you also state your parallel lines. Then afterwards, you also go for the T if there exists some tangent in the diagram. Then you also apply some theorem, Then you also apply some theorem that you know about the tangent, maybe tan chord theorem, or tan is perpendicular to radius, or that one that is saying if tangent are drawn from the same point, maybe A, to some points on the circle, then those tangents are equal. Then lastly, which is that one of X, then whereby we said vertically opposite angles are equal. Then I think we can just use that in that question that I had just here on the screen, which is this. So we have this diagram right now in front of us on the screen, whereby we said the statement up there is saying that in the diagram below, the tangent KT to the circle at K is parallel to the chord NM, and the NT cuts the circle at L, and the triangle KML is drawn, then M2 is equal to 40 degrees and MKT is equal to 84 degrees. Then you go to your diagram, you check if there is a diameter there. Then you find out no. In this diagram, there is no diameter. Hence, there can't be 90 degrees that we are maybe going to say angle in a semicircle. Then you can just pass that theorem. Then you go in your DRCPT, you go for R, for the radius, if there is a radius in the diagram. So in this diagram, there is no radius. So there's nothing that we are maybe going to say a radius is perpendicular to tan, because there's no radius. There's nothing that you're going to use like isosceles triangle. There's no radius. Then in DRCPT again, you go for C, the cyclic quad. You check if there is a cyclic quad to apply those properties of a cyclic quad. Angles, opposite angle of a cyclic quad are supplementary, or the exterior angle of a cyclic quad is equal to interior opposite angle. So those are not there. But we can see that NMKL can form something like a bow tie, of which you can have something like angles in the same segment, or angles subtended by the same chord. So in this case, you can maybe mark by a pencil that N1 is equal to K1, angles in the same segment. M1 is equal to L2, angles in the same segment. Okay. Then you go back to DRCPT, you go for parallel lines. Oh, remember, on the statement, it was stated that KT is parallel to NM. Therefore, we can see that angle T is equal to N1 alternate angles. Why? Because KT is parallel to NM. And again, we can say M1 is equal to the whole of angle K, alternate angles. Then you state your parallel lines that KT is parallel to NM. Then what else can we use with those parallel lines? Okay, I think that's all I can see. Unless you also see some angles, you can let me know. Then from there, you can move to T, which is tangent, and
Sir?
apply in, sorry?
Hi, sir. Sorry to disturb. Did you say M1 is equal to angle K?
Angle M1.
Yes, sir.
Yes.
The whole of angle K.
Yes, because can you see if you move from that N to M, you move from to K, from K again to T, it forms that Z shape.
Yes, sir.
Can you see that?
Yes, sir.
Yes, then angle M1 is equal to angle K as a whole.
Okay. Thank you, sir.
You get it?
Yes, sir. I was just
Okay.
clarifying.
Okay. Thank you. Then we go for the T in our DRCPT, which is the tangent. Then you apply the theorem that you know about the tangent, which is the tan-chord theorem. So we have the tangent KT. Then we can also have that triangle KML. And then we can see that K2 is equal to Km, which is the tan-chord theorem. Then after you are done highlighting those theorems using DRCPT, you can simply now go to the questions and see if you haven't answered those questions. Then for 4.1.1, we can see that the question is requiring us to find the angle of size of K2, giving some reasons of why we're saying maybe K2 is something. So on the diagram, we can see that K2, and we already have said that using that DRCPT, that K2 is equal to M2, is 40 degrees. The reason is going to be the tan-chord theorem. Then we move now to 4.1.2, which is requiring us to calculate the angle of N1. So when we look at angle N1, who can maybe tell us what the size of N1 is?
It's 64 degrees.
64.
Yes.
Why and how? Because you need to put some statement and some reasoning.
No, say it's not 64. I think it's 64 minus 40 degrees.
64.
Minus 40 degrees.
This angle right here is 84, since they've said right the MKT. Yes, it's 84.
Oh, so it's 84 minus 40 degrees.
So 84, which is the angle K as well. So you are saying it's 84, yes. 84 minus 40, then you are getting what? K1, right?
Yes.
Yes, and then that K1 is equal to N1, angles in the same segment. Yes, that's correct. And then you go to 4.1.3, calculate the angle of T1.
Sir?
Sorry? Yes?
I don't understand. How did you get it?
N1.
Yes, sir.
Okay. In this circle, can you see this diagram NMKL, the one that I was talking about of something like a bow tie shape? Okay, let me maybe do this. Can you see what I've drawn here? Can you see this?
Yes, sir.
Yes. So if this is a circle, and you have this shape in a circle, note that this angle is equal to this angle. Reason being, angle subtended by the same chord, or angles in the same segment.
Okay.
Also, this angle is equal to this angle, angles in the same segment, or angles subtended by the same chord. Do you understand this?
Yeah, that part I understand, sir. And my
Okay.
confusion is the calculations.
Okay.
Because
then now let's look at the diagram. The diagram that I was drawing there, can you see that this diagram here in this circle is NMKL?
yes, sir.
Yes. So we were required to find N1, right?
Yes, sir.
So if only you focus on that diagram that I was drawing there, this N1 is equal to K1.
Yeah.
Yes. And how can we get one? Yeah, how can we get K1? Because we have whole of K, like from M, K to T as 84 degrees, right?
Yes.
And then we already found K2 here as 84 minus 40. I think it is 84 minus 40 is 44, right?
That's the part that confused me. Like, how did you get 40? Because I think you said for K1 is equals to 40 degrees, 10 quad
No, no,
theorem,
no.
right?
K2 is equal to M2 is equal to 40
K2 is equal
degrees.
to M2.
Yes.
How?
This is the turn chord theorem. If this is the circle, this is the tangent that touches at one point. And then this is the triangle that we are having. And then this angle here is going, okay, this angle is between this chord and the tangent, right? Then you're gonna
Yes,
go
sir.
for the angle that is opposite to this chord that we are focusing on, which is that one. Therefore, those angles are equal.
Oh, oh yes. Yes.
Do you understand this part?
Yet also we are not, but 4.1, it is not K1, we are solving for K2.
4.1, we wanted K2. So
Yeah.
K2, you can see is between the tangent and the chord KL, right?
Yes.
So it's
I
gonna
thought
be
we were
equal.
solving for K1. The
Oh,
numbers
oh
aren't that
no,
clear. Sorry,
oh
sir.
no. Oh, sorry, we were solving for K2.
Okay. I was confused because when you said Tenkot theorem, I was like, it's not on
Oh no, no.
KL.
Oh
Yeah.
no, no, no. We were referring to K2.
Okay. Okay. Thank you,
So,
sir.
okay, cool. So you now agree that K2 is that
Yes, sir. Yes,
it's
sir.
40. Yes. Now we went for N1. N1, we said N1 is equal to K1. And we don't know what K1 is. We have to find it
Yes.
by saying the whole of that K, which is 84, minus K2, then we will get K1. Do you agree?
Yes, sir.
Therefore, our K1 will be 44 degrees.
Yes, sir. Yes, sir.
Yes. Then now after we got this K1, you go back to this diagram, this one, whereby in this case is Km and KL. I mean NM, KL. Then N1 is just going to be equal to K1. Then we already have K1, which is 44. Therefore, N1 is going to be 44, your reason being angles in the same segment.
Okay. Thank you, sir.
Yes, cool. It's a pleasure. Then 4.1.3 requires us to calculate the size of angle T. Here is T right here, outside of the circle. How do you guys think we can calculate for that angle T right there?
Sir,
How do you all think we can calculate the size of the angle T?
we can use
Alternate angles.
Sorry?
alternating angles, sir.
Okay, then angle T is equal to?
N1.
And then N1 was 44. And then reason being,
alternating angles KT parallel to NM.
Yes, that's what I wanted to hear. After stating your reasoning, state also those parallel lines. Then we are also required to calculate the size of L2 here. How do you think we can find the size of the angle L2?
Sir,
How do you think we can go find the size of angle L2?
we can once again use alternating angles.
To find what? To find L2.
Yes.
So L2 is equal to what angles?
No, we can say M1
Okay.
is equal to angle K,
Yes.
alternating angles, NM is equal to
It's parallel. It's parallel.
what did I say? Oh yes, parallel. Sorry, NM is parallel to KT.
Yes.
And then oh wait, sir. Can't we use angles in a triangle? Because we have K1 and M2. Oh no, but it will give us the whole of
You are coming good with the angle M1. Okay, I agree is equal
M1
to angle K,
angle
angles,
K.
alternate angles. Yes.
Yes, and then oh, M1
Yes.
is equal to L2 angles in the same
Exactly.
segment.
Exactly.
Oh.
Exactly. Then you got it. Do you all understand it, guys?
Yes,
I
sir.
can only hear
Yes,
the
sir.
voice of one person. Okay, thank you. Then the last question, which is 4.1.5, we are required to calculate this angle of L1. Now, angle 1. So how do you all think we can find a size of angle L1? What comes to your mind?
Can we use angle sum of a triangle?
What triangle? Which one?
Isn't it we already know the value of K1 and the value of M2 and L2?
Okay, yes, we have K1, we have M2, we have L2, and then what do you think?
So maybe we can use angle sum of a triangle to calculate the value of L1.
Which angles maybe are you going to sum up here?
Maybe we'll say 180 plus, okay, angle MKL.
Angle MKL. Okay, which is K1. Okay.
Oh yeah, plus angle M2
Okay, yes.
plus angle KLM,
Okay.
which is L1.
Sorry?
I meant angle KLM, which is angle L1 plus L2.
Okay. Then that is going to be equal to 180 degrees. The reason being a sum of angles in a triangle are supplementary.
Yes.
Then from there, you just substitute and then you find your L1.
Yes.
Just like that, and then you collected all full marks. So any questions that you might have, guys, for the sessions that we just had?
Sir,
Is there any question that you guys have now regarding what we just talked about?
sir,
Sorry, yes?
With regards to M1,
Yes, M1. Okay.
since it's equals to angle K, it means that M1 is equals to 84, right?
Yes.
So the whole of M is going to be 84 plus 40.
Plus 40. Yes.
Okay.
Yes. Yes. Any other question, guys? Okay, I guess
So,
there's no
sir,
question. Okay, yes.
so when we use the 10 chord theorem, like should the triangle always touch the circumference of the circle?
Yes. Those 3 points, those three corners of the triangle should always touch the circumference.
Oh, okay, thank you, sir.
Yes. So I'm not sure if you guys usually get some homeworks, because I'd love to give you guys some supper. Is Mr. Desmond still in here? Hello, sir.
Can even add with a breakfast for the next day.
Okay, so where maybe should I send it?
I think can send it to me via WhatsApp inbox, then I'll forward it to the group.
That's not a problem, sir. I will definitely do so.
Okay.
Yes, I thank you all for being with me for tonight, and let's meet again next time, and have a good night. I think that's where we'll end for today. Thank you, Mr. Desmond.